Okay, section 3.5, we're going to finish this one up today. This is division of whole numbers. And the first thing we're going to do is going to feel like, same song, second verse, to what we did in subtraction, is we're going to take a look at our properties and note, get it over there too, whoops, there we go, which properties will hold for division, okay? So remember, closure, it's your favorite, right? Closure means that if you take two numbers and some kind of in this operating system, so we're taking two numbers in the whole number system, and we're using this operation, which is division, do I get another whole number? Okay, so if I take a whole number and I divide it by another whole number, will I always get a whole number? No, this does not work. And can you give me an example? We'll do Savannah. 21 divided by 8 is not an element of the whole numbers, right? It's not a whole number. In general, it doesn't work. Now, are there some that do? Well, of course there are some that do, but that's not the point. The point is, does it work all the time? And the answer is no. Commutative. Does the order matter when you're doing division?
Yes.
Yes, it matters, which means this property doesn't hold, right? So this is a no. Can we do an example of where this won't work?
6 divided by 4.
Okay, 6 divided by 4 does not equal 4 divided by 6. True? Yeah. So the commutative property doesn't hold. How about associative? So I'm going to do associative because it's a little tricky to sometimes get it all to line up the way we want. It's going to fail as well. So here's an example. If we did 12 divided by 4, and then we divide that by 2. So what is 12 divided by 4? 3. And 3 divided by 2, well, it'd be 1.5 if I was doing it, right? Like that would be 1.5. And so let's try this other order. So if I do 12 divided by 4 divided by 2, well, what's 4 divided by 2? 2. And what's 12 divided by 2? 6. And these two things are not equal. So this fails. An identity property. Is there an identity element for division? Okay, so if we think yes, what's the identity element?
1.
Okay, so if we do the number 1, so if we do, let's say, any number 5, we'll do 5 divided by 1, we get 5. That is part of what we need to be true for the identity element. There's a problem. You have to go the other order as well. And what is 1 divided by 5? It's not 5. That's exactly right. It's not 5. So we don't get this one either. If we had a way to describe this, you could say that it's almost like half an identity, right? It works one direction, it doesn't work the other. And it happened the same thing with subtraction, right? Where we had it working one direction with the number 0 and it didn't work the other direction. So that's what's going on there. We also have division by 0. We had this property happen for multiplication that we need to check for division. If you divide by 0, or divide with 0, we kind of run into the same problem that we just ran into. One direction works fine. What's 0 divided by, say, 2? It's 0, right? But if we try to do 2 divided by 0, this is undefined. I should put this as undefined. You can't take 2 and divide it into 0 groups or divide it among 0 people. It doesn't make sense. It is an undefined, illogical kind of description, okay? The last one, the distributive property. The distributive property is interesting because kind of like the last two, it half works as well. So it depends on the direction. So let me give you an example. This is going to be a no. It's going to work one direction and not the other. So if I did 20 plus 10 and divide by 5, like this, this actually is going to equal 20 divided by 5 plus 10 divided by 5. And we'll check it to show that it works. But what's 20 plus 10? 30. And what's 30 divided by 5? 6. Okay. What is 20 divided by 5? 4. And what is 10 divided by 5? 2. And that's also 6. So it works in this direction. So kind of like the last two. There's one direction it's not going to work. So I'm going to highlight this and shift it over. It's not going to disappear, but I'm going to move it. So let's try the one that doesn't work now. So let's try the same thing, 20 divided by, and we're going to do 10 plus 5. So we're going to do the addition at the end instead of at the beginning. And if we try this, this will be 20 divided by 15, which is not a whole number. But if we tried to do it on the other side and sort of check it, 20 divided by 10 plus 20 divided by 5 would actually work really nicely. What's 20 divided by 10? 2. And 20 divided by 5? 4. This is 6. And on the left-hand side, it's not 6, right? Like this thing, whatever it is not equal to 6. It's not even a whole number, in fact. So it works in one direction, but it doesn't work in both directions, which is what it takes for it to be a property, in this case for distribution. So we have lots of properties for addition and multiplication, and we have none for subtraction and division. Right? That's what we actually have, is nothing. None of the properties work for subtraction and division. So we're going to do some algorithms then for, there's only 2 algorithms for division that we're going to take a look at. The first one is going to be our standard algorithm, and then the second one is going to be partial quotients. It actually has another name as well. It's sometimes called repeated subtraction, which we've seen that in the other modeling names, and so sometimes you'll see it called repeated subtraction. Let's look at the standard algorithm first, though. So the standard algorithm works like this. You take the first number and you put it underneath the division sign, or in the words of my children, under the house. Right? 623 divided by 5. So the part that's division is in front. We're dividing by the divisor 5. And you say something like this. You say, well, how many 5s are there in 6? How many times will 5 go into the number 6? And the answer is 1. So you put the 1 on top of the 6 because you're trying to put it into the number 6. And 1 times 5 is 5. And then you subtract. 6 minus 5 is 1. And then we bring down the 2. And we repeat that process. How many 5s are there in 12? 2. So we put the 2 on top of the 12, right, where the 12 ended in the number 2 column. And 2 times 5 is 10. And then we subtract. We get a 2. And we bring down our 3. And you can feel free, if you would like, to actually draw the arrows where you're bringing things down. If it helps you to keep things lined up, that's fantastic. So we have 23. How many times does 5 go into 23? 4 times. And 4 times 5 is 20. We subtract and we get a 3. Now, there's nothing else to bring down when we're working with whole numbers. Now, if we were working in decimals, we could continue going, bring down a 0 and put a decimal point in, but we're not working with decimals yet, okay? So, and we won't this semester. It's a different class. The 3 is where we end, and this is what happens when you're about 3rd, 4th grade and you're doing divisions like this. And so what happens at the end is you say that your answer is 124. That's the number you got that came out evenly. And then you do R3. Do you remember that? R3. What was that? Remainder, exactly, for remainders. So there's 3 different ways to do division, to be honest. This is one of them. This is the first one that kids learn, which is the curriculum level that we're working with right now for the most part. And then you move on into decimals and fractions. There's a decimal and a fraction version of this answer as well. But this is the kind of answers we're going to be working with, remainders. Okay? So a remainder of 3. Now think about what you actually have to do in order to do this problem. Well, first of all, you have to know your multiplication facts. And yes, we would prefer, I would prefer that every one of you know your multiplication facts, and I would pretty much guarantee that some of you don't, which is what it is. I would love for my 3rd graders and 4th graders in the midst of learning them to really get them down strong and know them, and that would be ideal as well. The reality is, though, that whether it's because a kid doesn't work hard enough to do it or whether they have a learning disability, there are some kids who won't know their multiplication tables. And so specifically, I'm going to focus on the learning disability ones because those are the ones that are going to benefit the most, I would say, from the next method that I'm going to show you. Okay? So this works really well when you know your multiplication tables. The other thing that works really well is if you're dividing by something that's a whole number. So, not whole number, excuse me, a single digit number, I mean. So I divided by 5. So if you know your multiplication tables of 5, that's great. But if you were dividing by 32, it's not as easy to do because you don't have a multiplication tables of 32 in your head, and neither do I. So if you're dividing by something that's a multiple digits out there, it becomes a much more difficult question than it was on this particular problem. So let me show you the other one. This is called partial quotients. Partial quotients hinges on the idea of repeatedly subtracting something. Okay, we're subtracting something. And we're going to subtract whatever the base that or whatever the divisor is that we're dividing by. We're going to be dividing by 5. So we're going to be subtracting things like 5 and 50 and 500 and 5,000 and 50,000. You're always going to be subtracting a 5 with trailing zeros. Okay, so whatever you're dividing by, you're subtracting that number and potentially some zeros after it. Okay, everybody with me? So you do not want to take 623 and subtract 5 and 5 and 5 and 5. You'll be subtracting 5 for quite a while before you get down to a remainder 3. Agreed? It'd take a while. Yeah? 100 and something, wasn't it? 124 times it would take you to subtract the number 5 before you'd get down to the remainder of 3. And you'd probably make a mistake somewhere along the way because you're doing the repeated process so many times. So what we do instead is we take our 623 and we subtract the 5 in the place value location that's the biggest place it can be subtracted from. In other words, I can put it under the 6 and it will work, so I will. And then I have trailing zeros afterwards. Okay? Now, what is this number? Well, this number is not really 5, it's 500, right? So what this really is, I'm going to jot this down to the side, is this is 500s. Right? I have 100 times my 5. Okay, so we're going to subtract. This gives us 123. I can no longer subtract 500, right? That's too big. So the biggest number that I can put, or place value I can put the 5 in now is in the tens place. I can put a 5 here, and I can put a trailing 0, and I subtract. So 123, so the 3 will subtract. 12 minus 5 is 7. What I really did is I did 5 times 10. That's what 50 is. It's 5 times 10. And I can do that again, actually, because 50 will still be able to be subtracted from the 73. I get a 23. Again, that's 5 times 10. Now, I'm writing down 5 times the side. If you just want to write down the 100, the 10, the 10, that's okay too. Right? That would be just fine. We'll come back to those numbers in a minute. I can no longer subtract a 50, right? But I can still subtract 5. So I'm going to subtract 5. So this is 1, 5. So I'm 5 times 1, or you can put just the number 1. This gives me 18. I can subtract a 5 again. Gives me 13. I'm going to come over here, my 13 here. I'm going to subtract a 5 again. That gives me an 8. Another 5. That gives me a 3. And at this point, I have gotten a number that's too small to keep subtracting a 5 from. Right? Single digit number at the end. I'm done. And if you go back and you capture all the things that you did, you have 100. Hang on, let me make that thicker. You have 100, 2 tens, so that's 20, and 1, 2, 3, 4, 4. 124, remainder 3. Okay, so drawbacks. It's a little time consuming. And honestly, the bigger the number, and I don't mean the more digits, right? Like if this number were, 1124, that's not really any more difficult than 124. But if it says something like, 199, that's really annoying. Okay, it's kind of like what happened when we were looking at some of our other things where we were like, how many times are we going to have to do this? Egyptians, that's the one we were doing. How many symbols do we need to write? Well, we need to write 9 of them. How many times do we have to write 9 of them? Well, there's 9 scrolls, and there's 9 heel bones, and there's 9 sticks, right? Like the repeatedness of it is a little bit cumbersome, right? Same thing here. If I have to repeatedly subtract something too many times because they actually get like a 9 in here or an 8 in here, it's kind of annoying. But the payoff, or the benefit rather, is that I don't have to know my multiplication tables to make this work. Okay, and in particular, this is the partial quotients strategy or repeated subtraction strategy. So if you were asked to do partial quotients or you were asked to do repeated subtraction, it's only base 10 values that are highlighted in yellow, and that is only the things you're able to use. You can't get to the end and say, oh, well, I don't really want to subtract 5 one time and one time and one time and one time. I want to do it 4 times. Nope, you're out of luck. This is the strategy you use. This is the way this strategy works. Does that make sense? Okay, so this is the partial quotient strategy. Okay, let's take a look then at some examples that are a little bit more interesting. There's one of them that's going to be like our coin example, I believe. It's the second one. Yeah, that's our coin example that you had an example of in your homework today. So we're going to look at won. So Juan saved $5,340 in 3 years. It says if he saved $95 per month the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? So this is kind of combining some of the problem-solving stuff that we did back in chapter 1, right? Problem-solving strategies, with some of these ideas about multiplication and or addition or subtraction, division, and so forth. So kind of a combination kinds of a section. Okay, so taking a look at this, what might you do for your first step?
Divide both of the numbers.
Okay.
Multiply 95 times 12, right?
Okay, so why do you want to multiply the 95 times 12? Because that's what I was thinking too.
Because that's what we know. That's how much we know like that. Now times 12 months.
Okay, so that's a guaranteed information that we know. We know he saved a certain amount, $95, for each of the first 12 months, right? So this first step that we do of 95 times 12, because it's the first year is 12 months, is a pretty good place to start. So this is 95 times 12. And as I start that one, let's actually do that one. We'll do practice because we haven't seen these now for almost a week, some of them, maybe more. And we're going to do lattice multiplication. So that's what I'm going to choose. So lattice multiplication is where we put the single digits on the top and on the side. Okay, so we don't write them down their place value, we just line them up. And then we cross and strike through each of our boxes, and then each of our boxes is a multiplication factor. So 9 times 1 is 9, 5 times 1 is 5, 9 times 2 is 18, 5 times 2 is 10. And then we extend our diagonals. And we start in the bottom corner, bottom right-hand corner, that's a 0. Remember, it's only things in the box that get counted, none of the extra 9, 5, 1, or 2 on the outside. My next diagonal is 5 plus 1 plus 8, which would be 14, right? Okay, so we're going to put a 4 down here, and we're going to carry a 1. Then I have 1 plus 9 plus 1, which would be 11. So it's 1 here. Technically carry a 1, but it's a 1 up here. So this will be 1140. Now, there's nothing that said you had to use lattice multiplication here, but you got to do something on paper. This is not a calculator exercise, right? The whole section that we're working in, this whole chapter, is how do I add, subtract, multiply, and divide. So if you grab your calculator, you're defeating the point, okay? So choose a method, do the multiplication, and it can be the standard method if you wish, unless you're indicated to do otherwise. And so 1140. So now what? So he saved 1140 the first year.
So I subtract that from the 5 up here.
Sounds good. So his $5,340 is how much we know he saved. And he saved $1,140 in the first year. So this will be how much he would have had to have saved in the second and third year combined. This subtraction is really friendly because it doesn't have any regrouping necessary. So we don't need any, additional strategies or any of that, like there's no borrowing or anything like that. So I just subtract down 4 and 4, 3 and 1, 5 and 1. We've got 4,200. Okay, so this 4,200 is the last 2 years, what he saved. How do we figure out how much he spent, or how much he saved per month?
Divide by 2.
Okay, so you can divide it by 2. That's a good thing to do. Why might we want to divide it by 2? Because that's not going to answer the question exactly, but it's going to get us a good step of the way there. So why divide by 2?
Because it can go into 4 and 2. I feel like I have to long.
Yeah, no, that's a good reason. Dividing by 2 is really nice. It's very friendly here, right? Because it does divide by 2 very easily. Why would we want to divide by 2 for the sake of the problem? It's representing for 1 year. So we could figure out how much he saved in 1 year. It doesn't get us the month part yet, but it divides really nicely by the number 2. So it's a really good step to do next. So if we take 4,200 and we divide it by 2, 2 goes into 4 perfectly, right? You don't have to do any kind of manipulation on the division or anything. So this is 2, and I've got a 4, and there's a 0. I bring down my 2, and it goes in 1 time. And there's a 2, and it's a 0. And then I just have the zeros that show up on top. So 2,100 is how much he saved per year for the last 2 years. Then what? How do I find out how much it is per month? We divide by 12. And now, could you have divided the whole thing by 24? You could have, but dividing by 24 is not as friendly as dividing by 12, honestly. And dividing by 12 is not terrible because 12 tends to be the multiplication facts that students memorize. So 12 is not a bad place to put us in to divide by at this point. I am out of space, so let me shrink this a little bit. So we're going to divide 2100 by 12. Okay, so you could do this with repeated subtraction for the sake of time. I'm not going to. This goes in one time, and this would be 12. And if I subtract, I have 9. It actually goes in 7 times next. And I realize I'm cutting things a little bit short, but I want to make sure you guys get time for group work. So it goes in 7 times into 12. So 7 times 12 would be what? Huh? 840. 84. Right? And then I would subtract.
Sorry, yeah.
That's okay. And then I have 60, and it goes in 5 times, right? Yeah. So this one's not so bad. So we would actually be saving $175 per month. Okay, I think, let me just run through the next one real quick. We've already seen a version of this question today, but it's pennies instead of dimes. Dan has 4,520 pennies in 3 boxes. He says there's 3 times as many in box. The first box is the third, and then there are twice as many in the second box as the first. So it's all based on the third box here. The first box has 3 times as many, and the second box has twice as many as box 1, so it's 6x. And then if I combine all these together, I have 3x plus 6x plus x is going to equal my 4,520 pennies. This is 10x on the left. And dividing by 10 is very nice. It ends up just canceling out the last 0. That only works dividing by a 0 in the denominator, right? Like a 10 or 100, we can only cancel zeros out that way, nothing else. This gives us 452. And the question is, how much money is in each box? Well, this is box 3. So there's 452 pennies, which means it's $4.52. And then if I go back to box 1 and I triple it, again, I know I'm shortcutting this a little bit, but I want to make sure we get to things finishing up. So this is 356, and box 2, which doubles that, is 2712. And again, you should show work here. So you're doing the multiplication out by hand in some fashion of the methods we've used. Okay, but I want to get to the mental math and the computational estimation, even if we don't get to group work and we do that as a take-home activity. Breaking up the dividend. So mental math, remember, mental math means math I can do in my head, okay? The estimation means it's an approximation. I can still write it down. But mental math, something I can do in my head. So the first strategy is called breaking up the dividend. And breaking up the dividend occurs when you see multiples of the number present in the number you're dividing. So 9 actually goes nicely into 63. It's one of the multiples of 9. And so is 18. Okay, so when you see that happen, breaking up the dividend is a good strategy. And what it means you're doing is you're breaking this up into, in this case, 6,300 and then 18. So in a very real sense, you're dividing 9 into 6,300 and 9 into 18. Well, 63, 9 goes into 63 7 times. So this would be 700, right? Because it's going into 63. And then 9 goes into 18 2 times. So this is 702. So you're easily able to separate them because the place values match nicely. The next one is similar, but it's less obvious. So when you look at 425, 5 does not go into 4. It goes into 25 just fine, but it doesn't go into 4. Are you with me? Do you have an idea, RJ?
Sorry, 5 goes into, what was it, 100, 20 times, but then we multiply the 20 by 4, we get 400.
Okay, so we're going to break it apart in a similar fashion to what you're thinking. Yeah, so if I break this apart, normally we wouldn't say that 5 goes into 4, but 5 does go into 40, right? So if I think of the number 425 as 400 and then 25, I get that same kind of twos like you're thinking of when you're thinking of how many twos, like it goes up to 20s. So the 400 still ends up being broken apart from the 425, and 5 will very nicely go into each of those. So 5's not going into 4, but 5's going into 40. How many 5s are in 40? That's 8. And then I have the trailing 0. And how many 5s are in 25? 5. So I have 80 and I have a 5, so I have 85. Okay, so you're breaking it up, you're doing the division, and then you're combining them back together. Those are the 3 steps essentially that we're doing. Yeah.
I think I was thinking of it differently, but yes.
Okay, that's okay. There's other strategies. This is just the breaking up division. This is the breaking up the dividend strategy. Computational estimation, again, means that you're going to get an approximation. Okay, so you want to look for something that's conveniently divisible by 4, because it says divide by 4, but it's close to the number. Like, we just can't randomly change it. It has to be close to the number we started with. So what is a number close to 4132 that's nicely divisible by 4? Don't overthink this.
32.
No.
4,000.
4,000, yeah, which I think is probably where you're headed. 4,000, right? This number right here at the beginning is already a 4. So if I change this to something that's close to it, and I use the number 4,000, that's pretty convenient, because 4,000 divides by 4 very nicely. It's going to be 1,000. So this number is approximately 1,000. So the purpose, again, for computational estimation really is that you should be able to look at an answer and say, well, I know my answer is going to be around 1,000. And so then when you actually do a problem and you get something that seems like way far off, it should red flag you. You should look at this and go, oh, that didn't make any sense. I was expecting it to be about 1,000, and instead I got it to be 125. Okay, oh, look, I missed the 0. Oh, I was off a place value. That's the point of computational estimation. Not necessarily to give us an answer, but to be able to check and see, did our answer make sense when I actually did something out longhand? Are you with me on that? Okay.